All right, so let us continue with logistic regression. Yeah, but by the way, I should warn you from the beginning that logistic regression is not actually a regression; it is classification, right? So it's a bit of a misnomer. Right? So this is logistic regression is a model for classification. Right? So the idea here is to somehow modify linear regression so that it will work for classification. Right? So the core idea here is that we want, if we have some, let's say two classes, we want to separate them by a linear boundary. And so we want to come up with a straight line. So in 2 dimensions, it's going to be a straight line that just separates them. Something like this. Well, but there are many different linear boundaries, right? So we could do this linear boundary, or we could do this linear boundary, or we could, I don't know, do this linear boundary, and so on and so forth. And it is quite clear that even if we find a straight line that with like the best possible separation, I'm not sure what this is here. It is quite clear that it is impossible to separate them perfectly, these two classes, but I guess it should be possible to separate them like almost perfectly. So maybe in a way so that so there are just 3 misclassified, right? So on the left, this is misclassified, and on the right, these 2 are misclassified. But still, imagine that this straight line, so if we change it just a little bit, it's still going to separate the 2 classes perfectly, right? So the question is, so which of the 2 is better, right? So how do we know which of the 2 is better? And what we're going to do, we are going to first try linear regression to do it, right? So if we change our 2 classes into zeros and ones, so we can fit a linear regression, right? So that I'm going to denote L of x, right? So the linear regression, so these ones and zeros are numeric values, and we are going to fit a linear model that approximates these ones and zeros. However, there is a bit of a problem. I mean, so what we are going to do, of course, these are just zeros and ones. So what we are going to say that we are going to come up with this classifier that it's going to output 1 if our L of x is bigger than 1/2 and 0 otherwise. So it is exactly 1/2. It doesn't matter. So it can be either of 2. But the problem here is that we cannot really, so this, since we are fitting a straight line, right? So it looks like this probably. So let me maybe try to plot it, right? So if these are our 2 axes, well, suppose that we just have one predictor, right? So not forget about this iris data set. So suppose that we just have one predictor, so x, and we have our response variable y, and our response variable can be either 0 or 1. And so if this is going to be, let's say, 1, so the observed values, so let me say, so zeros are going to be, say, I don't know, crosses. So these crosses are going to be zeros, and I don't know, so these dots are going to be ones. So these are our observed values. Now, but then if we are going to fit a straight line into this, it is going to look like this, right? So which means that our straight line, so the possible values of our linear regression, so possible predicted values, are not between 0 and 1, right? So that there is no such restriction in linear regression. And this is bad because what we really want is to have probabilities rather than just raw values. So what we really want is not a straight line, but something that looks like this. And the idea is that instead of predicting probabilities, we can take some transformation, right? So so probabilities take some values between 0 and 1, and we are going to apply some transformation to these probabilities, so that the output of that transformation is between negative infinity and infinity. And this is what it looks like. This transformation, so the idea is that this transformation is some function phi of p, such that if p changes from 0 to 1, then phi of p changes from negative infinity to infinity, right? So it is probably an increasing function, so the exact shape of this function is not really that important. So it could be whatever you see on the screen, or maybe it could be something like this. So as long as it changes from negative infinity to infinity when p changes from 0 to 1, we are going to be good. And people came up with one such function that is called log odds or logit transformation, right? Now, this is our function. So if this is our function z, then the idea is that if p changes from 0 to 1, then z is going to be changing from negative infinity to infinity. Yeah, you can see. I'm going to plot this so that you will see that it is really the case. But before I do, let me do some very simple calculation, right? So what I want to do, I'm going to solve this for p. So this is an expression for z in terms of p. So what if I turn it around and I want an expression of p as a function for z, right? So first I'm going to apply the exponential transformation to this. So the left-hand side becomes p over 1 minus p is going to be e to the z. Now I'm going to multiply by 1 minus p. So then I'm going to get p equals e to the z times 1 minus p, which is really e to the z minus p e to the z. Now I'm going to move this term to the left-hand side. So the left-hand side becomes p plus p e to the z equals e to the z. Now I'm going to factor out p. So this is p times 1 plus e to the z equals e to the z. And then solving for p, I get p equals e to the z divided by 1 plus e to the z. And this is called the logistic function. So here is our log odds. And the inverse function to log odds, right? So the function that we're going to get if we flip this about the line y equals x, right? So where is the line? So I guess the line y equals x is a bit tricky to see here because the scale is different. So the origin is here. And the line is probably, this is the line. So if we flip it about this line, then we are going to see this. It's the so-called logistic function. Yeah, maybe it's a bit not precise. So the word sigmoid means the shape. So there could be different sigmoid functions. So anything that has the same generic shape that looks like this is a sigmoid function. So this is a particular example of a sigmoid function, which is called logistic function, logistic sigmoid function. It is probably the most widely used type of a sigmoid function, but it is not the only one type of a sigmoid function that we use. Okay, so here is a little quiz for you.